This is Mona Mohammadi. I'm a moderator for today's talk, and welcome to the third session of our Global NMR discussion. This week we have the honor to be joined by Dr. Sami Jannin. He is a professor at UCBL, and before starting his position at UCBL, he did his PhD and postdoc at EPFL, yes. He is currently head of Hyperpolarized Magnetic Resonance Laboratory at UCBL and deputy director of CRMN, or Very High Field NMR Center in Lyon, France. Today he is going to talk about Dissolution DNP, and we also have a panelist who is here to help answer your question. Contesh is a PhD student at the European Center for High Field NMR in Lyon. As you might be familiar with our format, we are going to take a short break. We usually take a short break to answer your questions during the presentation, but today we are going to have 2 breaks to answer your question during the presentation, and then any question that is remained we can answer after the presentation. Okay, take it away, Sami.
Okay, thank you. Thank you, Mona. Hello, everyone. Thanks for joining the tutorial. It's a great honor to give this tutorial lecture on Dissolution DNP, and yeah, thanks a lot to the organizer. It's a great and very timely initiative, so I'm really grateful. I hope this will continue actually and go on forever. So I'll give a 35-minute tutorial on Dissolution DNP, and the objectives are to summarize the basic principle of dissolution DNP and review some applications, a limited number of applications. And then I'd like to present some of the hardware and the state-of-the-art methods of dissolution DNP. And at the end, I will just highlight some of the most exciting and interesting recent developments that I think are somehow announcing the new metamorphosis of dissolution DNP into a new version. Okay, so here's the outline. We'll talk about the genesis of dissolution DNP, and we'll see that it's actually not so simple. We'll review a limited number of applications. We'll talk about hardware and methods. And then we'll talk about new developments in dissolution DNP, and at the end we'll have plenty of time for questions. Okay. Okay, so the introduction will be brief, but I just want to remind everybody that dissolution DNP was really born from let's say the lack of sensitivity of magnetic resonance, and that despite the high field NMR magnet and the cryoprobes, there's still some sensitivity issue, and it's getting more difficult to get more sensitivity and more expensive as the years go by. However, this sensitivity is very critical for many applications, so it's usually really worth getting a factor 2 or 3. And so, to make the story short, dissolution DNP was invented in 2003 in Malmö by a group with Klaes Kohlmann and Jan-Henrik Ardenjahl-Larsen, and they showed that they could enhance the NMR signal in the liquid state by factors exceeding 10,000-fold. And the first demonstration was done on urea, on naturally abundant C13 urea, and they showed that they could record in a single scan a spectrum with really high sensitivity that they could not record even after a few days without DNP. So the principle is the following. So you want to polarize a target nuclear spin, for example, C13 on the molecule of interest. And the first thing you have to do is bring an electron spin. So you use what we call a polarizing agent, which is often an organic radical, the molecule that has an unpaired electron. And so the first step is to actually mix the radicals and the molecules of interest together. And so you put your molecule of interest at the highest concentration that you can afford, for example, or it could be a mixture on other molecules. And you add electron spins at a concentration which is typically 10 to 50 millimolar. And sometimes you need to add a glass-forming solvent, for example, water glycerol, which is well known from the solid-state DNP community, what we call DNP juice. And when you freeze that mixture, it should form a good glass. And this will usually ensure that you have a good distribution of the electrons and the molecules of interest. And so now when you bring this sample to low temperature, usually DNP is done at around 1 Kelvin to 1.5 Kelvin. And in a moderate field between typically 3 to 7 Tesla, you can achieve an electron spin polarization which is really close to 100%. And then you shine microwave at a frequency which is really close to the center of the electron spin resonance, and you transfer polarization from your electron to the nuclear spin. So I will not talk about this in detail because it has been already nicely explained by Monu in the first tutorial. It would be hard for me to continue without giving a few important names. For example, Overhauser came up with the idea of polarizing nuclear spin by shining radio frequencies on electrons. So this was in '53. Then Charlie Schlichter, the same year, who made the first demonstration. And then there are a lot of people that I should cite, but I thought maybe I will keep it short to three person. So Abraham, who really developed DNP in non-metals. Maurice Goldman, who developed the theory of thermal mixing, which is one of the important DNP mechanism at very low temperature. And then maybe someone who is not often cited, but I'd like to mention Borghini and Mongo, who came up in '69 with an experiment which is almost the same as the one we do today. So they showed that they could do DNP in frozen liquids. And they didn't use glycerol at that time. They used butanol and water. And they didn't use nitroxide or tempo or tritiol. They used porphyrexide, which was already a nitroxide radical. And they did DNP at 1 Kelvin and 2.5 Tesla, and they obtained about 40% polarization on protons. So if you go back to this paper, you'll see that it's actually very, very close to what we're doing today. And it was done about more than 4 years at the CERN in Geneva. Okay, so you do DNP at low temperature and moderate field. You polarize your nuclear spins, and then if you switch off the microwave, of course, then because you have all these electron spins, you start to have some paramagnetic relaxation that kills your hyperpolarization. And in dissolution DNP, what we want to do is to measure the sample in the liquid state. So we want to turn this low temperature frozen sample into a liquid state sample. And one way to do that we've been doing for a long time since the invention is actually to melt the sample and at the same time to dilute it with a hot solvent, which is usually water. And when you do that, you dilute it, then you have less radical concentration after dilution, you have less paramagnetic relaxation, and you can transfer it to the NMR spectrometer. And one thing that we've been doing all this time, which is very important, is that you dissolve your sample while it is in the cryostat, in the high field region, because since you have all these electrons, if you try to take your sample out without melting it and diluting it, if you go to low field or if you go to high temp in the solid state, you tend to have a very, very efficient relaxation that can be on the millisecond time scale that will kill your hyperpolarization. So here's the patent that described this invention, where they mentioned the need of a cryostat or a field of a means to polarize the solid, which is a microwave source, and a means for dissolving the solid polarized material. And an important point here is that it is said that it has to be done while the sample is inside the container in the cryostat. Okay, and if you do that, you can actually preserve a large part of the polarization. And then transfer it rapidly, because then you have a nuclear spin relaxation that is on the order of seconds or tens of seconds in the liquid state. So you have to transfer it rapidly to your NMR spectrometer or your MRI machine. Okay, so here's a video already shown in the past. This was at the time I was in Lausanne, so it just shows how you load your sample in your sample cup, and then you put your sample cup in a sample tube, which is a way to rapidly change the sample. And the sample is rapidly inserted in the liquid helium environment in the cryostat at around 4 Kelvin. And when you do that, you shock freeze the sample in liquid helium. And then you can start to pump on the helium bath to cool down to 1 Kelvin. You can turn on the microwave, set the power and the microwaves, etc. And then you can observe by NMR how the polarization builds up in the solid state. And this may take minutes or hours depending on your sample and your spins. So this is the liquid state NMR spectrometer with an injector. It has a means to inject the liquid sample in the NMR tube. And it's going to be connected to a dissolution stick here with a pressure cooker where we heat up 5 ml of water to a high temperature and high pressure. And after the water is warm, we're going to do something a bit crazy. We're going to bring this stick down in the cryostat and couple it to the sample. And once this is done, once this is coupled, you can press a button and release the hot water on the sample. And thanks to high pressure helium gas, the sample will be pushed out in the liquid state out of the cryostat and will be transferred to the NMR spectrometer in a matter of a few seconds. So now the stick is brought down, the button is pressed, and there is a set of valves that open and close to push the sample out. And the sample goes in here, this magnetic tunnel, and then is transferred and automatically injected in the NMR spectrometer, and the NMR experiment is automatically triggered, of course, because you don't want to lose any time. Okay, so that's all for the let's say the basic principle. So we could do a short break now if there are any questions. Mona, I think there are no questions in the Q&R.
Yeah, I don't see any question in the Q&A, but if you have any question for the first part, now is the time to ask. If no, we can move on to the next one. Yeah, let's wait like 10 to 20 seconds if anyone has a question. So yes, the first question is from Dimitri Woodke. What is the microwave frequency?
Okay, so the microwave frequency depends on the field. So it's if you're at 3.35 Tesla, it's going to be around 94 gigahertz. If you're at 6.7 Tesla, it's going to be around 188 gigahertz. So these are the two main fields at which we're working. We also have done experiment at 5 Tesla, which is 140 gigahertz.
The next question is from John Blanchard. He is asking how much improvement between 4K and 1K.
Okay, so because the electron spin is already substantially polarized at 4 Kelvin, we don't get the Boltzmann factor as an enhancement. So usually you get typically a factor. When at 7 Tesla, you typically get a factor 2 improvement between 4K and 1 Kelvin.
The next question is that what should be the properties of the hot solvent for dilution?
I don't have a lot of experience on that. We use water most of the time. We've been using some other solvents from time to time, but it's mainly water. It has a big heat of of fusion and a bit bigger heat capacity, so it works really nicely with water. But there are many other solvents that have been tested by other groups. The Friedman group, for example, has worked on. I think it was, I don't remember, it was an alcohol, but I don't remember which one. So it's in principle, it's possible to use other solvents, but water is the one that is mostly used because it's what proteins and humans like.
And the next question is that how much time currently is needed to reach the NMR spectrometer?
So yeah, we'll talk about that. It can take between a minute. If you do it manually and you inject it manually in a human, for example, it can take up to a minute. And if you do it with an automatic system with fast valves and fast pumps, then it can take around a second, 1 or 2 seconds, typically.
What can be the interaction? I think it was, I'm sorry, intrascan delay during the NMR experiment after the polarization.
Sorry, I didn't hear you, sorry.
What can be the intrascan delay during the NMR experiment after the polarization?
So, I mean, in the NMR spectrometer, you can bring the interscan delay very short with the problem that you're going to destroy your polarization every time you pulse. So, but if you pulse with very small angle, you can do many pulses in the liquid state. But then if your interscan delay is too short, then you don't have enough acquisition time, so your resolution gets lower. So the standard is to leave at least a second between each pulse to leave enough time for acquisition and to have a decent resolution in the liquid state. So that's the kind of standard way of doing liquid state acquisition.
Okay. So the next question is that why does the sample have to be dissolved inside the cyrostat instead of, I think, the polarizer? I'm sorry, inside cyrostat inside the polarizer. Benomier's bullet does not comply to that, right?
Yeah, I mean, sorry if I said that it's wrong. I mean, it's one way to do it, but Benno has shown another way, and I'll come back on that at the end of the talk. So yeah, it doesn't comply, but it also works.
Okay, the last question is that 40% polarization of 1H, does it mean that we can reach enhancement of 660 times 40%, which is 660 is the gyromagnetic ratio between 1H and electron?
Okay, sorry, I have to understand the question.
So the question is that a 40% polar P of proton 1H, does it mean that we can reach enhancement of 660 times 40%? 660 is the ratio of gyromagnetic ratio of between 1H and electron.
Well, I don't really get the question. I mean,
you can read the question in the queue, I think, maybe.
So when you talk about an enhancement, it's interesting to know, yeah, the enhancement is with respect to what? With respect to the DNP condition, we never get an enhancement of 660. I mean, we usually get an enhancement of 100 or 200 at low temperature. But then when you melt your sample and you compare it to room temperature, the enhancement is 10,000 or more. But in the solid state, actually, the enhancements we get are not that impressive compared to the enhancement you get in MAS DNP. It's just that we are 100 times lower in temperature. But
and the next one is, what is the typical recording time of the solution spectra, and what is the range of nuclear T1 relaxation?
So the range is the same range as the T1 of the nuclear spins when they're not hyperpolarized. So for protons is around a second. Some isolated protons can have T1s that approach 10 seconds, but it's usually around a few seconds. For carbon-13, it's around 10 to 60 seconds. And for nitrogen-15, it can go up to 10 minutes. Same for lithium, or low gamma nuclear spins tend to have long T ones and are easier to address with dissolution DNP.
Okay, so I guess we can now move on to the next part. Any question that is remaining, we can answer after the talk.
Good, thanks. Thanks a lot for all the questions. Okay, so now we'll have a look at the hardware and the methods. So there are 3 steps. One is to polarize the sample. The other one is to melt and transfer the sample, and finally to acquire the sample after injection in the spectrometer. So I'll review briefly the different types of polarizer that have been built by companies. So the first one was the Hypersense. I think there are more than 40 machines installed worldwide. I don't know how many are actually functional now. The Hypersense works at 1.5 Kelvin, 3.35 Tesla. So the microwave frequency is 94 gigahertz. The sample volume, I think, is about 40 microliter. So 2 drawbacks today are the helium consumption, which is about 50 liters of liquid helium per week, and the service, which is, I think, very limited today and also costly. Then came the Spin Lab by General Electric. My numbers might be a bit wrong, but I think there are more than 20 installed worldwide. The machine operates at slightly lower temperature, 1 Kelvin. I've even seen data below 1 Kelvin, 5 Tesla. So the microwave is about 140 gigahertz. And in this machine, which is really dedicated to clinical application, you can have 4 samples polarizing at the same time. And each sample is 1.6 ml. So it's really a big volume for human applications. The machine is cryo-free, so it recycles helium. It's made for sterile use. And the 2 drawbacks from the point of view of an NMR spectroscopist is that it's very expensive, plus also each polarization is costly because you have to change the fluid path. And this is something I'm not really sure, but I've heard customers report failures of the fluid path. So it seems that there's still some hardware issue on the dissolution side. Then the third one, which has been built by a company, is the Bruker functional model. It's a polarizer that has been installed in 3 different sites, and I think that's the end. It will not be installed anywhere else. It works at 1.2 Kelvin, 7 Tesla, which is, I think, the highest field. So the frequency is 198 gigahertz. It has some features such as modulation of frequency, microwave gating. The sample is not really big. It's 250 microliters, so it really aims at NMR applications and preclinical, but not clinical applications. It includes some of the most recent features, such as cross polarization at low temperature, and it also enables to change probes from carbon to nitrogen to phosphorus. The main drawback is the very high helium consumption of this machine. And I think, I'm not sure I can say that, but since we're on the internet, it's very safe. So I think there is a cryo-free version in preparation for this machine. In addition to that, there are actually many equipments that have been home built. Starting, for example, from the one of Matthias Ernst in the ETH, which is noticeable because it was, I think, the first one that had a multi-sample feature. So this was back in 2012, and they already had 6 samples that would polarize and be dissolved in the machine. In 2017, I think this is the first home-built cryo-free dissolution DNP machine. There was the Spin Lab, but this was the first cryo-free dissolution DNP machine home-built by Lloyd Lumata. And then there are several others. For example, there is one in Paris, on which I was involved with Geoffrey Bonenhausen and Mathieu Baudin. One in Lyon with Morgane Cellier in our lab. one in Cambridge with Arnaud Comment, and one also in DTU with Jan-Henrik Larsen, with a company called, I think, Hyperspin. So now I'm going to show you how the DNP and the dissolution and the microwave radiation works. So all of these polarizers, they have a magnetic field and a means to cool the sample, the cryostat. And in the cryostat, you have a probe, and the probe has a sample space where you can insert your sample. There's a microwave waveguide that brings in the microwave, usually in an oversized mode. So usually it's a tube, it's an oversized circular waveguide that allow you to bring down the microwave. And some of those cavities, I mean, we call them cavity, but they are just basically a box. They have some gold-plated reflective structure that allow you to really try to concentrate the microwave field on the sample. And then you may have a coil. Some of them have a coil to actually just measure the NMR signal, to measure the carbon-13 buildup. And this is one of the first version of our coil that we have been using in Lausanne and now in Lyon, that has actually 2 nuclear spin capabilities, so proton carbon, in order to do a double resonance experiment, such as CP. Now, if you look at the state-of-the-art performances of DNP in these conditions, one of the most used radical is the triethyl radical. It has a narrow line, and it's very efficient to polarize carbon-13. So if you work at 3 Tesla and 1 Kelvin, you typically get about 40% polarization in about a few hours. So you see here, it's 10,000 seconds would be about 3 hours. And you can get this polarization if you add some gadolinium. Usually you add 1 or 2 millimolar of gadolinium to boost the polarization. Now, if you go higher in field, for example, here 6.7 Tesla, this is Andrea Capozzi at the TTU, who reports up to 70% polarization with a build-up time of 30 minutes. So after 1 hour, typically you get 60 to 70% polarization at best with 1 millimolar. Oh no, yeah, with 1 millimolar gadolinium. So you can really get polarization that are not close, but almost close to unity on carbon-13 in an hour or so with the triethyl radical, which is quite impressive. You can also use nitroxide radicals that are widely used in MAS DNP. But if you do that, even at high field, so 6.7 Tesla, you get only 30% polarization with a build-up time of 30 minutes. So nitroxide radicals are not good for polarizing carbon-13 directly. But what we've been working on in Lausanne, together with Jeffrey Bonenhausen and Aurélien Bornet, is how to improve the polarization of protons, and then to use the CP, which is widely used at MAS DNP condition. So you can improve the proton polarization by using frequency modulation. So you just need to modulate the frequency at a certain rate on a certain range, and this allows you to get about 90% polarization on protons at 6.7 Tesla. So you really get a proton polarization close to unity. And then you can try to implement CP at 1 Kelvin. It's quite difficult because you're in superfluid helium and you have problems due to heat and arcing. But if you manage to do it, you can then transfer the proton polarization on the carbon-13. And we've been working on that for a few years, and I'm going to show you how that works. So you shine microwave for some time, and then you apply a CP sequence, which is basically a 90-degree pulse, a spin lock, and a 90-degree flip back. And you do that on both proton and carbon. Here the 90 is an adiabatic 90 because the lines are broad and we don't have a lot of B1. And one trick is to actually stop the microwave irradiation before you do the CP. Why? Because if you stop the microwaves, the electron spins, they go back to thermal equilibrium. And thermal equilibrium is 99 point something % of polarization. So all the electrons are polarized, and when they're polarized, the paramagnetic relaxation is almost inexistent. So all the spins are frozen in a way, and there's no flip-flop going on. So if you do that, you don't have any efficient T1 row relaxation mechanism. So you can do CP for a very long time. So you can do CP for example, 20 milliseconds and you reach a plateau. Whereas if you don't stop the microwave, during the CP, you have paramagnetic relaxation and you reach a plateau after a few milliseconds. So if you do that, if you stop the microwave briefly during your CP, you get a very efficient transfer. And now if we take all these ingredients together, so the high field, the microwave modulation, the CP, and the gating, it's a lot, but this is what you get. So you need your coil, you need your sequence and your modulation. And instead of having this very slow carbon buildup with the nitroxide radical, from time to time, on the blue curve, you see you increase the polarization substantially because you do your CP step. So you wait for the proton to be polarized, you do a CP, and then you wait and you do another CP. And that way you can reach about 60% polarization with a build-up time of 3 minutes. So after 10 minutes, you get typically 50 to 60% polarization in our polarizer. And so this brings now DNP to I mean almost the highest theoretical possible value, but also with a time which is actually almost too short. And you're not going to do an MRI experiment every 3 minutes, but it might be interesting for an MR spectroscopy, because if you want to have high throughput and do an MR experiment often, then that might actually turn to be very useful. Okay, so the next step is dissolution and transfer. Once you have reached your high polarization, you want to turn your sample into a liquid, and the usual way to do it is to bring the dissolution stick that we have shown in the video down to the sample. And so in this dissolution stick, you have a capillary that will bring the hot water on the sample. And then there's another capillary to let the sample escape. Usually you use 10 bars and about 450 K. And this is enough to rapidly melt the sample, and then you can collect the hyperpolarized solution. So this may seem simple, but it's not so simple to melt a sample that is at 4 Kelvin in a superfluid helium cryostat. So there have been a lot of work done by the Jan-Henrik Ardenjahl-Larsen group to study how this melting process works. You should avoid steam, you should add a nozzle to improve the jet impact. The temperature has to be optimized, the pressure, also the flow rate, you don't want to go too fast. And there is a nice paper by Sean Bowen and Jan-Henrik where they show the profile of the concentration of the hyperpolarized sample at the output of the polarizer. So you make sure that you recover the sample in a reasonable amount of time. But recovering the sample is one thing, but what we want to recover is the hyperpolarization. We don't want to lose the polarization during the transfer. And then after transfer, we want to be able to inject it in a way that is stable and repeatable to do the NMR experiment. And so there's a few interesting papers. I may have missed a few, but Sean Bowen and Christian Hilty have worked on an automatic injector with a syringe pump and with some valves that are borrowed from the HPLC. And there's also one reported by Walter Kochenberger. I think there's also one by Lucio Friedman that I did not cite here, but a few groups have been working on trying to improve this transfer in injection. So I'm going to briefly show you what we have in Lyon. So the idea is that you dissolve your sample and then you go in a valve and you fill a loop. So you fill a loop that has a certain volume. So you can select the volume you want to bring to your NMR tube. Once the loop is filled during the dissolution, there is an optical sensor that will then trigger the rotation of the valve. And when the valve turns, there is a liquid pump. So we have a very high flow, high pressure liquid pump that can push the sample very rapidly through a magnetic tunnel. The idea of the magnetic tunnel is that the solution does not go to very low field. It has to stay in a field, a certain field. In this case, it's about 0.9 Tesla or so. So the magnetic tunnel sustains a high field, and then you can inject it in a home-built injector. This is, for example, the injector that was built by Morgan Cellier in our lab. And once the NMR tube is filled, you turn another valve to pressurize the tube with helium gas in order to stabilize the NMR, the solution, and also to avoid bubbles, that there is some degassing that happens and that may cause trouble for the NMR line widths. So this is just one hyperpolarized spectrum that I show. It's acetate, so it's really a standard that we often use to check that the system is working. So it's C1 labeled acetate. You see here some of the glycerol, naturally abundant C13. So the enhancement is typically on the order of 10,000 or more. And here you see the line widths measured every 5 seconds after injection. And you see that very rapidly, the NMR line widths go below a hertz, typically 0.5 hertz. And this is measured directly after the transfer with this whole system built by Morgan. The transfer in this example was done at 4 meters per second. So it takes about 2 seconds to 2.5 seconds to travel 10 meters between the two machines. So one interesting thing with such fast transfer is that you can address nuclear spins that have T1s on the order of the transfer time. So the next step, of course, is to look at protons and fluorine and other nuclear spin. Okay, so now I will briefly review very few applications. That's not the point here, but I just wanted to do that because I think it's interesting, especially because there are some new applications that are coming up these last years. So I want to just spend three slides on that. So this is the application that most of us know very well because it's really a driving force in the field. It's molecular imaging. So here, people hyperpolarize a small metabolite such as pyruvate, and then the pyruvate is injected, in this case in humans, and then by localized spectroscopy, you can see how with time the pyruvate gets into a certain voxel and how it is transformed into other metabolites. And here it's transformed into lactate here in the tumor region. Whereas in another region, which is not presenting any tumor, there is a lower uptake of pyruvate and no visible conversion into lactate. So that's one of the main applications now, is to be able to detect pathologies in vivo, such as prostate tumors in humans. But there are also other applications that are being developed in the context of NMR spectroscopy. I'm just going to cite a few. I'm sorry for those who I don't cite. We've been working with Patrick Giraudot from Nantes on trying to apply our methods to metabolomics. And we have shown that you can actually measure very complex extracts like cancer cell extracts or plants or biofluids with a high sensitivity, but also with a high repeatability. So with a CV of about 5% between each samples, which is already very good, but this is actually being pushed even further by Patrick and his team in Nantes, who just got an ERC grant to develop this theme. Another field of research is drug discovery, and there are many papers. Many of them are by the Hilti group. I just cite one review because he reviewed all this work in this paper. You can polarize ligand, you can polarize water, that then transfer polarization to ligand, and then measure how the ligand binds with a protein. another interesting field of research is to look at chemical reactions with, for example, short-lived intermediates, or to look at polymerization, etc. Then I can cite also the work of Dennis Kurzbach in Vienna, who just got an ERC grant to investigate the polarization of proteins with hyperpolarized water. So in this experiment, you have a protein waiting in the NMR tube, and you polarize water, and then you put water on your protein, and by exchange, you actually manage to polarize the protein itself, and then you can do either proton COSY or proton natural and Natchez QC, etc. And this is something under investigation in Vienna, but also in the Weizmann with Lucio Friedman, who is also actively working on this topic. There's a very interesting recent paper on hyperpolarization of RNA, for example. And finally, I want to show you some results that were obtained by Jean-Nicolas Dumez, who also got an ERC grant recently to work on hyperpolarization of complex mixtures. And here in this particular example, he's shown that he could do ultra-fast dosing. So you could do ultra-fast, like sub-second measurement of diffusion in some mixtures together with hyperpolarization. So I don't want to go deep into these applications, but just want to show you that it's something that is really exciting, and it's very active now. And there are many people who are starting to work actively on these applications. Okay, I guess we could make a short break for question, Mona, now before we go to the last section.
Yes. Okay, the first question is that, can this technique be used for paramagnetic proteins?
That's a very good question. I don't know. I guess you'll have an enhanced paramagnetic relaxation at nearby the paramagnetic sites, but I don't see why. I don't see why it shouldn't work.
And then the follow-up question is that, can the paramagnetic metal affect the polarization gain of the nuclei of the coordinating ligand and reduce the gain from DNP?
Okay, so if you have a paramagnetic protein and you want to measure the binding with a hyperpolarized ligand, then I guess it may affect the relaxation of your ligand and increase your contrast, I guess. Yeah, that's
I may just add a comment, Sami.
Yeah, please.
Is that few people, if any, have polarized by DNP proteins directly in the polarizer, because you will then rapidly heat them and probably destroy them. So what has been done up to now is to polarize water and transfer to the protein, or polarize ligands. So maybe we were thinking of polarizing the protein directly, which would be very difficult first because you will destroy it. And then if it is paramagnetic, you will have extreme relaxation during the transfer.
Yeah, thanks for, I did not get the question this way. So thanks for, yeah. So polarizing the protein is very easy, but then to have the protein survive during the dissolution and transfer is another story. But if you have a protein with sufficiently long T1s and that can survive the temperature jump, then why not? But I guess that's maybe not the best way to go. Water is a good polarization reservoir.
So the next question is that, so normal electron flipping is thermally activated. I lost the question, sorry. Is thermally activated rather than referring to temperature independent statistical fluctuations?
So what's the question?
He's asking
John,
that no.
John, I don't get it. Normal electron flipping is thermally activated. Do you mean in the DNP or in the liquid state? Or?
I can unmute John, I guess, so he could ask his question.
I've been thinking about his question for a while, and in fact, I think I understand what he means. Or maybe you can ask it now that you're unmuted.
I'm curious to see what the compound thinks that I'm asking, but so you were saying that that by turning off the microwaves, you eliminate these electron spin flips because they're largely frozen out at these low temperatures. However, I guess a thing that we've been thinking a lot in our group, recently, is that there's this inherent spin noise due to the fact that square root of the number of the electrons will inherently be fluctuating around. And so I'm just wondering how cold one has to get such that you're limited entirely by this sort of quantum mechanical effect rather than the thermal fluctuation effect.
Yeah. I don't know. I know that the main mechanisms is the electron T2, the electron spin spectral diffusion, the flip-flops between electrons, and that there is a very nice dependency on temperature and let's say electron polarization and relaxation. It goes with 1 minus p electron square. So we going to 1 Kelvin. Down to 1 Kelvin, it nicely follows the curve. So I guess we're not there yet.
Yeah, but so basically it's good enough because you're already hitting 50, 60, 70%. So yeah, if it was 90 versus 92%, it wouldn't really matter that much, I guess.
Yeah, and the electron polarization is 99.8 something, I guess, in our conditions. So it's so much polarized that the 1 minus p square is really close to 0.
I guess maybe the real question is as a result of the uncertainty principle, you have to have some fluctuations in the transverse direction. And I'm curious if that starts to have any effect at these temperatures.
Yeah.
Which maybe that answer is far in the future to worry about.
Yeah, or maybe you have an idea of an experiment that could.
I'll think about it and get back to you.
Okay, so the next question is that why do you have the paramagnetic relaxation only with microwave on during your CP? When you stop the microwave, the electron do not disappear in principle?
Yeah. No, so yeah, the electron do not disappear, but when you give time to the electrons to repolarize, to relax to thermal equilibrium, they have less relaxing power on the nuclear spins.
The next question is that how do I'm trying to find questions that has not been answered. Is it possible to implement long-lived states for DNP experiments on paramagnetic proteins?
Is it possible to implement long-lived states for DNP on paramagnetic proteins? Why not? I mean, you can implement long-lived state on small molecules. This has been done. Even hyperpolarized, you can implement long-lived state on proteins. This has been done. If you have I think there are a few papers by Vassos, for example, and Heliman Sarkar, where they have shown that they could excite long-lived state on proteins. So if you can polarize a protein with hyperpolarized water, you could potentially excite a long-lived state. Yeah. I don't know why, but yeah, that might be possible. Yeah.
And the next question is that in the case of pyruvate injection, how do you avoid the injection of your polarization agent together with pyruvate, which will be in the sample with pyruvate even the low dissolved concentration?
Yeah.
How to avoid the... Go ahead.
So for trityl, one way to do that is to change the pH and to make a precipitation of the radical and filter the radical and then we adjust the pH. In case of tempo, it's a bit more difficult. What you can do is quench or scavenge the tempo with vitamin C. We have a paper on that where you use vitamin C to scavenge the tempo, but still you have the non-paramagnetic form of tempo that remains. And another way is to use materials where the tempo is covalently attached. And, we have a series of material that's called hypso. There are silica-based porous materials that are used to actually circumvent this issue of having free radicals in solution. So the radicals stay attached on the material itself and can be filtered.
And how to avoid the problem of relaxation in the case of imaging, as the recording of MRI image takes mostly minutes and the nuclear relaxation is in the second range, and therefore the hyperpolarization effect will become.
So there are schemes for fast imaging. So you can acquire an image in less than a second. It's, for example, there are fast sequences that are routinely used with hyperpolarization. So this is not something that I know how to do, but there are groups that are really expert on that.
So I guess because we are limited in time, we can move on to the next part of your presentation and then answer the remaining questions later.
Okay, so thanks again for all the questions. Okay, so now I'm going to go back to one of the first slides. When we describe the dissolution DNP process, we say that we need to mix the radical with the molecules homogeneously, bring the temperature down to 1 Kelvin, and then polarize the nearby nuclear spins with the electrons. And we said that if we stop the microwave, or if we warm up the cryostat, or if we take the sample out, the paramagnetic relaxation kills the hyperpolarization. So because of that, we need to melt and to dilute the sample inside the polarizer. And because the relaxation in the liquid state is on the order of a second or tens of seconds, we need to transfer rapidly the sample. So if we look closely at the DNP process, it sounds like every single step is a problem. And you need to mix homogeneously, you need to go to low temperature, you need to have electrons nearby that kill your polarization, that force you to have a very difficult melting and dissolution process, and then you have to be fast. So because of that, dissolution DNP has been limited in its applications and in its, let's say, democratization. It's been limited to a small number of groups that could have the hardware and the skills, etc. But I mean, since a few years, there are a few groups that are actually coming up with new ideas and new ways to reinvent dissolution DNP and to solve these issues. Homogeneous mixing is not required anymore, and I will show you how. You can have your electrons actually not nearby, but further away from your nuclear spins, so that you don't have paramagnetic relaxation anymore. It has been shown that you can do the dissolution actually outside the polarizer, and you don't need to be fast. If you do things differently, you can have lifetime of hours or even days. So I'm going to show you the work of Samuel Cousin and Theo Eldahay, who are working in my lab on polarizing matrices. I'm going to show you some of the work of Andrea Capozzi and Arthur Pinon from Jan-Henrik Arden-Jan-Larsen lab on UV-induced radicals. The bullet by Benno Meyer, which was mentioned, where the sample is rapidly ejected from the NMR, the polarizer. And I will briefly mention the work by Nobuhiro Yanai on triplet DNP on water. So this is an experiment that was published recently by Benno Meyer and colleagues. Here in the polarizer, instead of having a sample stick, they have a sample that has the shape of a bullet, and the sample is dropped down in the probe. And the way to eject the sample is with high pressure gas. So they have a line here with very high pressure gas, helium gas. I think it's about 10 bars or even more. And this will push the sample out through a line to the NMR spectrometer. And they have a dissolution duct here. So the bullet drops down in hot water, explode and melt, and then is injected in the NMR tube. And of course, during the transfer, if you don't want to lose the polarization, you have to go very, very fast. So they actually go within a few 10 of millisecond. I think it's well below 50 millisecond. And they sustain a field which is pretty high, 70 millitesla, to avoid both paramagnetic relaxation, but also something called nuclear thermomixing. So in the solid state at low field, you can have polarization flowing from one nuclear spin to the other via dipolar interactions, and this can actually kill your polarization. So this is something that, I mean, I thought was impossible. I think many people thought it was impossible, and they managed to do it. And they could get significant polarization preserved in the liquid state. And so this is really a game changer, because it really simplifies a lot the way you eject and you dissolve your sample. And it's all new. So this is, I think this has really the potential to change the practice of dissolution DNP, especially for NMR spectroscopy. So I'm really looking forward to what Benno is going to come up with in the next years. Another very bright idea is to use UV-induced polarizing agents. So in this experiment, Andrea Capozzi and Arthur Pinon, they form very small beads, very small pellets of about 10 microliter of sample, because then they irradiate with UV and they need the UV to penetrate. So that's why they have small pellets, but they shine UV on the sample. And if they put some molecules that can generate radicals out of UV, they can actually get tens of millimolar concentration of free radicals in the sample. And with these radicals, they can do DNP. So microwave on, microwave off, microwave on. You see the relaxation is fast when you turn off the microwave. But then the fantastic thing about these UV-induced radicals is that if you blow hot gas on the sample and you bring the sample above 100 Kelvin, then these radicals, they just annihilate, they disappear. And if you do that once the sample is polarized, then you end up with no radicals anymore, and you end up with a very long relaxation time, even at 4 Kelvin. So you get typically 10 hours on this particular sample. So that's something that might in the next year enable with this method transport. So now you could think of actually taking out the sample and transporting it in the solid state in a low temperature environment and bringing it to the point of use. So no need for hardware, no need for personnel, just a consumable that you can get from outside. In parallel, we had a very similar idea. We did not annihilate the radical, but we decided to put the radical in a different phase. So in this experiment, we, instead of putting pyruvate in the solution, we made a powder of pyruvate, a micro powder, and we impregnated the molecules of interest with a known solvent that contains the radical. So if you do DNP on the solution, you get a fast polarization buildup. But then if you add the powder, you see that the polarization takes more time to get in the powder by proton spin diffusion. And after a few minutes or hour, you get your particles polarized. And then you can transfer this proton polarization to the carbon in the powder. And because there are no electrons in the powder, and because carbon-13 spin diffusion is very, very slow, when you turn off the microwave and you warm up the cryostat to 4 Kelvin, you get a very, very long relaxation time. So on pyruvate, we could get 40 hours T1 at 4 Kelvin. And this is something that we could do on several molecules like alanine, glycine, glucose, etc. And so the idea that we actually managed to turn into reality was to take the sample out, put it in a helium dewar together with a small magnet, 1 Tesla Albach magnet in the helium DOR, and then store it for a night. And after that, do the dissolution in the DOR and get a significant part of the polarization preserved. So I think this is, together with the UV radical, something that is really promising, but it's very sample specific. So you need to have a microcrystals formulation with hydrophobic solvents that are actually toxic, or you need to have very small sample irradiated with UV, and the ability to create the right radical depends a lot on the sample. So what we are working on right now is to try to find a way to polarize virtually any sample, any molecule, any mixture, any complex mixture. And the way we do that is by synthesizing epoxy matrices that are porous and that contain the free radical. So you make an epoxy with the nitroxide radical inside, and you can get pretty big monolith that have a very high porosity. It's about 70% porosity. You can tune the porosity. So you have a material that is porous, that can be impregnated with a solution, and that has a lot of radicals in the walls. So not in direct contact with the solution, but still it can be polarized. So you can, for example, here prepare a mixture of urea, carbonate, formate, glycine, and in a few tens of minutes, you can polarize the solution that is inside the pores. And then if you switch off the microwave and go to 4 Kelvin, you have T1s on the order of hours, even 5 hours or more on these complex mixtures. So no specific sample formulation, just a solution that you impregnate. And then you can dissolve and filter the powder of the material and get hyperpolarized spectra without any radical. So this is currently under development in our lab, and we are trying to bring this to preclinical imaging. The final slide is about something that is a bit exotic, but I think very interesting and promising. It's the use of photoexcited triplet state. So instead of using a free radical, you can use, for example, here a pentasane derivative that is soluble in water. And in this paper by Nobuhiro, they have managed to excite this triplet state with green light, which give rise to a very highly polarized triplet state, paramagnetic state. And then by microwave radiation, they can transfer that to the water molecules. And this is done at 100 Kelvin, 140 Kelvin, because the polarization of your triplet state does not depend on temperature. So you don't need to go to very low temperature anymore. So this is not, I mean, triplet DNP has been around for decades, but I think this is the very first time that it's done in a context which seems compatible with dissolution DNP. So maybe in the next years, I mean, now it's quite modest, the enhancements are modest, but maybe in the next year it's going to become competitive with very low temperature DNP. So I just wanted to highlight this result that I find quite interesting. And yeah, that's it for today. I want to thank the entities in Lyon, the university, CNRS, DNS, the funding, ENR, so that's the French research agency, the ERC, also Brooker, in particular Jim Kemp from Brooker for his great support, and the whole team in Lyon who did part of the work that you've seen. And before questions, I just want to remind you that the Hype 20 conference has been canceled this year. So it's going to take place hopefully next year in 2021, same place, same time in Lyon. And yeah, thanks a lot. Thanks.
Okay, so we are a little bit over time, but we are going to take questions if Sami is happy to answer them. If you won't be able to stay longer, then you can watch the full video, the recording of this session on our YouTube channel. With that, I'm going to move on to questions. One more thing is that you can vote on questions by thumbs up, so I would know that which question has more people requested to ask. So one question is that, have you been able to dissolve the polarized microcrystalline periwet for liquid phase NMR experiments? Maybe you could try this with Reno bullet.
So you mean, have we been able to dissolve the microcrystal? Yeah. So actually, it's not more difficult to dissolve a micro powder than a frozen liquid. I think it's even more easier. If you look at the thermodynamics, it takes less energy to dissolve a powder than to melt a frozen glass. So yeah, we've done the experiment where we have dissolved I think it was glucose and alanine and some other molecules.
The next one is that, do you have enough microwave power at 3.3 Tesla to polarize using triplet state?
To polarize with what?
Using triplet state.
Yeah. Oh well, we don't have, because we have about 100 milliwatt, so it works well for thermal mixing DNP or cross effect. But in the case of triplet state, we would need much more power because we need to transfer in a few microseconds with a novel experiment or solid effect, integrated solid effect. So you would need maybe several watts or tens of watts plus a resonant cavity. So we're not there yet now. Today we can't do it.
The next question is that, is a micro powder approach same as DNP sense?
Oh yeah, it's very, very similar. And actually the idea came up thanks to the DNP sense community. I see the name of Aaron Rossini. I mean, he was in the office next to me when this research happened. So his input was very important. Lyndon Emsley and others. So it's very, very much inspired from the MAS DNP sense research. Yeah, absolutely. Okay,
I think I asked most of the questions, I mean all of the questions that were not answered. If there's no questions, then we can probably end the presentation.
Okay.
Okay.
So thanks everyone. It was a great pleasure. Thank you, Mona.
Thanks a lot for joining us. It was a great honor to have you here.